today. You know, we're doing a couple things all at once here, right? Over the next, say, roughly 45 minutes. The context is heat transfer, conjugate heat transfer, conduction, convection, radiation, a mechanical engineering challenge that a lot of us are faced with, wrapped around the application of conformal cooling. And we'll talk about that a little bit as well. But how do we, say, maintain a constant or narrow band of temperature in a mold, like plastic injection molding or any other similar type application or manufacturing process? And then we're going to be using a tool today to kind of tell the story, and that tool is Ansys Discovery. So Ansys Discovery is, I'll say, a relatively newish piece of software in the simulation space. And we're going to show some of its unique aspects, particularly around GPU, burst to cloud, and the context of what does it take to create a lot of data and why we would want to. So I've only got 2 slides today, right? This is supposed to be hands-on. So Yusuf, you said deep dive, so I'm thinking let's just get our hands dirty. But before we jump in, I wanted to provide a bit of context, right? So for those who are not familiar or relatively new to the term conformal cooling, what we're really talking about is a cooling circuit, so an internal fluid circuit that gets designed for, and in today we're going to be talking about plastic injection molding. So plastic injection molding, of course, involves usually a gigantic chunk or chunks of steel or aluminum. We're melting and injecting a liquid polymer, and then we're cooling that polymer so it solidifies. And we're doing that quickly. I mean, in plastic injection molding, we're looking at some cycle times at most, maybe in large parts, maybe a minute, and for some small parts, and today we're going to be talking about a pretty small part, we're talking about seconds. So this is what we would consider to be, I'll say, medium to high, potentially high volume production. So anytime we can make a design change to the tooling that can reduce potential defects or increase the quality of the part, we're talking about serious financial benefits, right? So whether you are designing a part for yourself, or you are working, say, at a mold house or a service provider where you're designing just, quote unquote, just the tooling, what we're going to show today is kind of a workflow of how you might want to approach that. And of course, anytime we're talking about conjugate heat transfer and keeping things cool, we talk about simulation, because hand calcs don't work for complex geometry, straight up, right? Everything we learned in school on heat transfer and statics and structures and everything, that works fantastic for rectangles and circles and cylinders, but the world is not made up of rectangles, circles, and cylinders. As you can see here in these pictures, the world is made up of some really complex geometry. So the key to designing an effective conformal cooling, say, channel or mold design, is you want to keep a constant distance between the molded part surface and the cooling channel. Okay, because the whole key here is we're trying to maintain not only a certain temperature of the mold so that we can optimize our molding parameters and our molding process, but also the temperature variation. We don't want one side of the part to be really hot, one side of the part to be really cold, because what's going to happen is as it cools, one part's going to cool more than the other, and all of a sudden we've got warpage, right? And that's as a result of, say, the coefficient of thermal expansion of the particular part. So we're talking about reducing warpage. We're also talking about designing a mold that's reliable. So whenever we have huge stress gradients in the mold, and again, I'm not talking massive, like hundreds of degrees. I'm talking maybe 10, 20, 30, 40 degrees. But if that happens in a really, really small space, and a lot of times we have designs that have small little shutoffs or little features. And if we've got a large temperature gradient in a small feature, we're talking about a lot of thermal stress. And as I mentioned before, in high cycle volume, high production, we're talking about cycles. So if we start cycling hot, cold, hot, cold, hot, cold, hot, cold, we're going to have reliability issues. The mold itself is actually going to start to fail, say, a lot sooner than we expected. So we're going to be reducing the thermal stresses in the mold itself if we can maintain a constant temperature. Now, some of the pushback you might say is, well, that looks really complex. And on the left-hand side, we've got this great graphic from Xometry that shows in the upper left-hand corner, we've got this more traditional red sort of circuit. And that circuit is generally manufactured by taking the block of steel, you CNC machine out the shape of the part, and then you drill in or you mill out these channels in X, Y, and Z, right? Because traditionally we had these CNC machines and we could only really do X, Y, and Z or an old mill. And so what you do is you drill in and then you'd plug it behind. So I would drill in this, plug behind, drill in this, plug behind. And so what I'm left with is this three-dimensional circuit, let's say, that goes around the part, but I've got a complex curvature part and I've got a bunch of X, Y, Z. It looks like an old video game, right? Like old Nintendo or Sega or something like that. So the limitation on that, on making that, was actually because of the way that we were machining the part. Fast forward a few decades, and we have the ability to machine or manufacture or fabricate some really, really complex or internal geometry. So what we're doing is we're saying, listen, the part I'm molding is complex. The cooling circuit should be complex. And of course, when we talk about complex geometry and complex internal geometry, like a cooling circuit, we're talking about additive manufacturing, right? Additive manufacturing is completely unlocked all of this new complex geometry, right? Heat exchangers. I know, Yusuf, even you've done a lot of promotion on the new additive manufacturing techniques and really complex geometry. We've shared some heat exchanger geometry, right? Triply periodic, minimally surfaced, gyroids. I mean, the aerospace industry, medical industry, right? We're doing a lot of really, really cool stuff in additive. The not so sexy part of it, conformal cooling, right? Like no one really wants to talk about it because it doesn't, it's not something you go to, you want to go to school for. I want to design molds, but at the end of the day, we're creating a very, very, very optimized and efficient cooling circuit, which can result in, some serious business value, some serious financial benefit. And so on the left-hand side at the bottom in this screenshot from Xometry, we can see that, if we were to compare, let's say, the thermal profile of this mold here with a traditional, say, CNC milled out cooling circuit, you can see that in some cases, the distance between the part and the cooling circuit gets really big. And that's also the area we see a hotspot because the cooling circuit's far away from the surface that we want to maintain. So we have this really inconsistent distance between the cooling circuit and that geometry. And as a result, we have the hotspots. If we could change that, and we will, and we do, then we can have a much more consistent thermal profile. So that, in a nutshell, is what conformal cooling is. We're conforming to the shape of the mold with the cooling circuit. So let's take that one step further. This is from the International Journal of Heat and Mass Transfer. We're looking at what are the variety of different ways now, right? So you can say, hey, I've got this cylindrical geometry. It looks like it's got a sort of a screw thread on it. I can conform to that geometry several different ways. I can spiral around it. Here I've got, looks like 2 inlets, 2 outlets, same thing on this side. Maybe this time I go circumferential, this time I go axial. There's so many different ways that we can create this cooling circuit geometry and try to maintain it. So what are the other ways we might optimize? So I'm here on the left-hand side, I'm optimizing for mold temperature. The other things I might be optimizing for are minimizing the flow rate, so I don't have to have as massive, minimizing the pressure drop, right? We have a fluids problem here because somewhere is going to be a pump and a working fluid, and that needs to go through this circuit. So I've got some physics in addition to the geometry. I've got some physics I get to optimize. Now, taking that one step further, because this middle picture is kind of boring geometry, this is the extreme. And Renishaw, which of course is one of the leaders in additive manufacturing, metal additive, right? Here's an example. Here we've got a cutaway, very, very complex mold. Perhaps this is a family mold. I'm not quite sure of the application, but if we peel that away and look inside, you can see we've got half a dozen different cooling circuits. Those cooling circuits, not only do they have different lengths and different locations, they get different diameters. So now what they've done is truly optimized. I mean, if somebody did their homework and it looks like they did, this mold could be operating within maybe just a few degrees of each other across the whole mold. So really, really incredible stuff. Something, we weren't able to really do. And the limitation really was just the fabrication method of the mold. So what are we going to do today? Well, we're going to simplify just a little bit. As much as I would love to optimize a super complex geometry with a super complex 3D conformal cooling circuit, we just distilled it down, Yusuf. We don't have that much time, but what we're going to do is we're going to analyze this, right? We're going to analyze this in Discovery, and we're going to look at how could we optimize this somewhat simplified circuit. Yes, I kept it planar, but we've got a couple bends in there. And I've got this small plastic injection molded cover part, which I actually reverse engineered for some curriculum for a project you and I worked on about 7 years ago. So you may not recognize it, but this part has been floating around for a while. And all we're trying to do is understand a couple things, right? One, we want to understand the heat transfer, right? So I've got a thermal load that's being generated by this part. Now, in real life, okay, in the molding process, what happens is I bring in a molten, if you will, polymer, right? And then it's solidified. So the initial temperature on this mold is going to be whatever the melting temperature is of that. We're not getting into that level of physics, right? So step one of creating a simulation, no matter what it's for, is understanding, can I simplify the physics without reducing accuracy? So I'm not going with the full phase change, melting to solidification and the amount of energy that takes, where we're kind of simplifying it just a little bit. Not only that, also, this is a transient thing. At time equals 0, I start, I've got my cooling circuit, I've got my temperature, and then I start cooling the mold. So we're not even going to do a transient here. I know. I hope you weren't looking for something super hyper, realistic here. But what we've done is I've actually calculated the equivalent thermal load, wattage, if you will, that would equate to how long it would take to cool this part in like 20 seconds, maybe 10. I can't remember the number I used. So what you can do is you can easily calculate. This is Excel math. This is linear math. We don't need simulation for this. Say this is the starting temperature, this is the ending temperature, this is the time, and this is the heat capacity of the material that I'm cooling. Real simple stuff, and I can convert that into a thermal load. I'm going to show you the model in a second, but I wanted to give you kind of an overview of what we were about to do in Discovery. So I've got a thermal load in here, and that heat being generated, that thermal load, has to get removed by the cooling system, okay? So I've got a thermal load that's going to be generated by this part, and then I'm going to conduct through the part. So I'm conducting through the ABS material of the part and through the steel of the mold, and then I'm going to be convecting through. There's a velocity, as you can see here. There's an inlet on this side. There's an outlet on that side. So we've got conduction, which is solid heat transfer. We've got convection, solid to fluid heat transfer, and then the third aspect of conjugate heat transfer is radiation. We're not accounting for radiation here. There's not a lot of radiation in this design. But in some cases, if we've got a really particularly hot mold, or we've got maybe not in molding, but if we've got some black bodies and some surfaces that are close together, we might see radiation. So I'm 2 for 3, if you will, on the conjugate heat transfer. In that model, we're also going to establish some sort of flow rate through here, and you can see we'll get some sort of flow profile in that cooling circuit, and then ultimately one of the key outputs of this model here is, what is the temperature profile in the mold? What is the hottest of the hot, the coolest of the cooled, and is there a way that we might want to control that? So does that make sense? Does that kind of, in a nutshell, bring us up to speed? Conformal cooling, really, really complex designs for cooling circuits and molds, which we have simplified just a little bit for this morning here. Okay, I'm going to move over to Discovery, and so you should recognize this geometry. And for those who are new to Discovery, Ansys's newest simulation product, I'll just give it to you kind of in an overview in a nutshell. If you're familiar with SpaceClaim, which might be a software that you've heard of, a CAD software, Ansys acquired it just about 10 years ago. So that is a CAD modeling tool. One of its strengths is, and I'll give you the background. It was designed by analysts. It was literally a CAD. Think of a CAD program. Put your analyst hat on for a second, your simulation hat on, and say, what are the things I don't like about a parametric CAD tool? And again, I'm a Creo guy. I'm a SolidWorks guy. I'm an Onshape guy. I've used NX. I've used CATIA. I mean, all of those kind of parameter-based, maybe sketch-based, if you will, or feature-based. They have a history, which is nice. It's great for creating production CAD. Not necessarily the right particular tool to do pre-processing for FEA and CFD, right? So for structures and fluids. So what SpaceClaim was developed by people who are like, there's got to be a better way, right? Which is kind of how all software starts, or all companies start. And their better way was to say, let's simplify the CAD modeling process. Let's go do direct modeling. So all the CAD modeling in Discovery is direct modeling. I'm directly pulling and pushing. There's only 3 tools available to modify the geometry. I'm not going to go into a full workflow for CAD. We're not, it's kind of out of scope for today. But the key to understand here is I've imported this directly from a native CAD program. So one of the key things here is in mold design, okay, it is extremely rare, if you are a mold designer, that you have access to the molded part in its native CAD file. A lot of times you're starting with customers' CAD data or a partner's CAD data. And 9 times out of 10, that's going to come in as a step file, right? Step and IGES, the two sort of internationally known sort of, common denominator geometry files. The reality is you do lose, and depending on the CAD import, maybe a tenth or a hundredth of a thousandth, and that can kind of add up sometimes. So it's kind of a pain in the butt. And sometimes if you're doing a lot of top-down design, so what I mean by that is in mold design and in plastic design, a lot of times we're doing surfaces and curves, and we're driving our solid geometry from other geometries, right? So think about a large team of people. One person's going to own the industrial design, that's the surfacing, and then other people, the engineers, let's say, who are more concerned with the physical stuff. So you've got this CAD file that's crazy. It's got edges, got surfaces, got solids, and a lot of times that's not a nice a nice geometry to bring into a step file or IGES file and then try to bring into another CAD. So this is directly from native CAD. I was able to easily strip out surfaces, edges, etc., and get a nice sort of mold design extracted out from the part design. And the fluid as well was easily extracted out. So we've got a very simple sort of fluid extraction tool that we can pull out. So we got volume extraction and we got enclosures for internal fluid flow and for external fluid flow. So this CAD design tool can actually do everything you need to do. Short of meshing, short of actually solving the problem. So this gives you hopefully an idea of some of the geometry that we pulled in here. Now, Discovery has kind of 3 different modes, if you will. The first mode is modeling. You can see that in the bottom of the screen. This is basically the new space claim. For those who are familiar, space claim is on its way towards obsolescence. We don't have a firm timeline. I hear it's pretty close. I know that a lot of the software and licensing in the background has already started to change over. So customers in the space claim world are going to be transitioning to Discovery. But as you can see, if you're familiar with how space claim looks, it's the exact same thing. We've got a few different things in the GUI, but ultimately, we got dark mode, for those who like to stay up late at night and model. So the second sort of capability or capability set, if you will, that's in Discovery, this is what's brand spanking new. This is what Ansys has been working on for quite a while and been developing. This is our GPU solver. So what we're looking at right now, and we just had a couple things change in the GUI. On the bottom right-hand corner, you see a dashboard for simulation. These are all our post-processing tools, and this is our play, power, solve, whatever you want to call it button, right? And then, of course, we've got our simulation tab. And so what we've got is we've got an entire environment where I've got my CAD geometry, I'm doing all my manipulation to prepare the model, and now I can apply my physics. And so this model I pre-built, I was considering building it on the fly, Yusuf, and I was like, you know what? I'm not quite sure if I'm ready to do that at 7 o'clock in the morning. Maybe if we moved it forward like 8 or 9 Chicago time, I would have had the gusto to do it. But I'm only on my second cup of coffee. I need, I think, at least 2 more to build it on the fly. We'll solve on the fly, so you can see the speed of the GPU. But ultimately, what we get underneath our CAD sort of model tree up here is our physics model tree, right? So of course, for those, I'm sure the audience here, you're familiar with simulation. So just to recap, we just have our material assignments, right? So I've got structural steel, plastic, ABS plastic, if you will, and then water for the working fluid. Gravity in this case is turned off. A lot of these narrow channel forced convection conjugate heat transfer models, we don't turn on gravity. It's free to do so. I suppose I could have. I am accounting for natural convection. And this is one thing that I think a lot of people who are new to heat transfer kind of forget. Natural convection, unless you're in space, which can be your case, right? We're not molding in space yet, but unless you're in a vacuum in space or are operating in an environment that's the same exact temperature as your mold, which is rarely the case, right? You're going to lose heat to the environment, okay? We are surrounded by a fluid, and we're not going to model the air in the molding house and the warehouse and the manufacturing floor here, but we need to account for the fact that all of these surfaces of the mold are going to be convecting and losing heat transfer. And so as we build out our physics for this model, this was actually automatically put in. So what we're trying to do with Discovery is sort of help train people to model things a little bit more accurately. And I've just added in 5 watts per meter squared, which is generally speaking like a still air, right? So, and then at an ambient temperature of 22 C. I've also added in the heat loads here. So I've got 160 watts. That's what I calculated as the equivalent heat load of what it would take to reduce this down. I think from the melting temperature of maybe it was 150, 170 or something down to ambient. And then I also have a small sort of heat load that's in the mold. Now, in a mold, we actually will have heating elements as well as cooling channels. It's really important to have the mold come up to temperature. We don't want to, put in molten polymer into an ambient temperature mold, because what's going to happen is it's going to freeze, literally change phase halfway through the mold. So we're very carefully controlling the temperature band of the mold itself. And so I've got these two thermal loads here, and this is just an equivalent thermal load that I kind of did a quick back of the hand calculation. So I've got 50 watts being generated within the mold itself, and then 160 coming off the part. And then we apply our CFD, if you will, or fluids boundary condition. So there's an initial temperature here that was put in by default. I just left that as ambient. We're not doing a transient, so this doesn't get taken account too much. We've got our inlet flow, which in this case, 0.25 kilograms per second. So it's converted to a mass flow rate. I kind of ballpark this. I mean, generally you might be around 0.1 or even 1, depending on the cooling system. And I've got that coming around 80 C. So we're trying to maintain some sort of temperature. And again, there's a whole sort of system and infrastructure in the back end with a heater and a pump and everything. And then generally speaking, we're going to have some outlet. I've got this set to 0 gauge pressure. In reality, it's not going to be 0 gauge pressure, because again, you've got a whole cooling circuit that's going to be out in the floor, and maybe even being shared with other molds depending on how it's done. So I've just kind of simplified it a little bit. Automatically, for those who are familiar with doing analysis on assemblies, we have to maintain some sort of interface or connection, if you will. And again, this was all automatically created. I didn't have to press any buttons for this. Automatically created bond of contact between two solids, which basically means, in our world, it means you're going to conduct from the part to the mold with no temperature rise. If I wanted to, I could edit this right now and say, oh, there'd be a small temperature rise, but in this application, there isn't. Same thing here. We've got a fluid solid interface. So this is really representing the boundary layer, right at the edge of the wall inside the cooling channel. And again, this is assuming sort of no temperature rise right at that surface. We can always edit that if we wanted to. So I left those relatively straightforward. Just for kicks inside of Discovery to show, there's also a structural model, so we can do thermal stress analyses and typical, quote unquote, typical FEA. There's as you can see, fluid and solid. There's also a sort of an EMAG side of things too, so we can do some antenna design. But ultimately, some fundamental physics, and the key is what happens when we hit solve. So all we have to do here is hit solve, and you know that when I say all we have to do is hit solve, those who are familiar with simulation know that what's happening in the background is we have to mesh the model or discretize the model. And in CFD particularly, that can take a while. So that right there was about 10 seconds, maybe 15 tops. And we're getting results out of a conjugate heat transfer, solid fluid interaction type model. That is insanely fast. Yusuf, thumbs up, thumbs down. How does that compare to a typical sort of CFD model, waiting for meshing, waiting for results? Not too shabby, right? So we're not. What was that?
Pretty fast.
Not bad. Yeah, maybe there's a delay on the video. I'm just going to pause it for a second because it's going to start using up the GPU. But so what we've done is we've essentially meshed it. I'll use that term, or discretized it through the GPU completely, right? So we're not doing hardly any work on the CPU. And it's using a voxel method. I won't get into details, but it's not a traditional sort of cell-based or finite volume-based approach. It's a brand new approach. It's one that Ansys has co-developed with NVIDIA to leverage, at first, the CUDA cores and the technology that NVIDIA has in their graphic cards. And then as of just a few weeks ago, because the latest version of this is the latest version that came out last month. Just a few weeks ago, Ansys announced that this is now starting to work on AMD GPUs as well. So we've got a vast majority of the marketed GPUs. And the funny thing about simulation is, if you're familiar, quote unquote, back in the day or in traditional CPU-based solving, I have to wait. And what I'm waiting for is the CPU to mesh the model. And then I have to solve those problems. And usually I've got this convergence I have to wait for. And then I have to send all of this information after I converge from the CPU to the GPU so I can render it and I can look at it, right? And so logically has been going on here is we're seeing GPU solving. Part of the reason is because I have to show the answer anyways. And also, we've got way higher performance out of the GPU chip technology. We've broken, we broke Moore's law on CPUs on transistor density a long time ago. But with GPUs, we get a whole nother level of compute density and thermal management, which is really, really exciting. So yeah, just in a few seconds, I'm able to get my temperature distribution spread out. For those who are interested on sort of the discretization, what I can do is I can actually zoom in and I can say, hey, this is roughly the mesh size. So for those who really, really want to dig in, I can float over the mesh size. And as you can see down here, I do have a fidelity control. This is about the extent of the control I have for mesh sizing. If I wanted to dig further, and for those who are analysts, myself included, who want to really understand what is the boundary layer, how are we discretizing the boundary layer, are we converging, what is my y plus, all of those sort of parameters that give me the confidence that the answer is right. All I have to do in this case is slide over to refine. This is the third and final mode, which I'm not going to really dig into today. I'm going to focus on the explore mode because it's fast. Is the refine? That's going to give me the level of control that I might want over mesh sizing, mesh quality, and I can dig in and start to extract it out. And then level 4, because there's always another level, Yusuf, of course, is up here in the upper right-hand corner. If my comfort zone is Fluent, like mine is, if I know the tools in Fluent, if I want to add in things like phase change, multi-phase, all that stuff, I literally can transfer this straight into Fluent. I've got all my materials, all my boundary conditions, all my cell zones, if you will, and from there I can start to add in more and more detail. So I think hopefully you can see that from a tool perspective, what Discovery is trying to do is introduce a lot of people who may be intimidated with Fluent. That phrase is used a lot, right? Or intimidated with some quote unquote hardcore simulation and put it right in front of them. Take away the meshing concept for those who are brand new to simulation, trust the discretization in the GPU, enjoy the speed. And then as you get more and more curious or more critical of the answers that you're looking at, then there's 2 different ways to dig deeper into the model and make sure that what you're doing is mathematically and physically accurate. Does that make sense?
Yeah, that makes sense, Jim. I have one question though,
Yeah.
about the physical, how you would call it, maybe accuracy. So you said like you just trust the GPU, but I'm wondering
Mhm.
how far are you off in terms of like this first result versus if you import it to Fluent and then actually run the calculation with cell zone refinement, checking the Y plus, etc. Like how far are we off?
Yeah, it's a great question. So there's a handful of comparison white papers, and I'll give you an example. Forced convection, this model right here, we can get within 5%, no problem. And it's just a matter
Okay.
of just getting your fidelity up there so you can capture the proper heat transfer coefficient right at the wall interface, and that's that. So
Has Ansys talked about the solver behind that technology?
they have.
They have. Okay.
And this GPU solver, and again, I don't work for Ansys, so I can't speak to any sort of core sort of intellectual property. But there's a lot of capabilities in Discovery because I may not be expecting to match this to test data per se,
Hmm.
right?
Hmm.
If I put a thermocouple on a forced convection model, which is simple physics, everyone knows is we're not trying to break, we're not pushing the limits of physics or math at all within a few percent. There's case studies of it matching Discovery to Fluent and Fluent to test. Okay, what's the average exit temperature here? Yeah, we get that within a degree, right? What's the exact heat transfer coefficient on this bend versus that bend? Maybe we're a few percent off here and there, right? But again, the level of engineering of digging into the exact local heat transfer coefficient is rarely done, right? What do we care about? What's the average temperature in here? Throw 2 thermocouples on. What's the outlet temperature here? Throw a thermocouple on. Excuse me. What's the flow rate? Right. I'm when I go to match the test data, I'm only putting 2 or 3 sensors on here, the most important ones. So forced convection, conjugate heat transfer without radiation, all good. This has radiation. I haven't seen white papers on radiation. We know it's a little more complex. It's T to the 4th, so there's a lot more kind of happening there, and there's 2 or 3 different ways that we can simulate that. So I don't, off the top of my head, have seen a white paper on radiation. But at the end of the day, if your physics are relatively simple, we're not doing evaporation, condensation, phase change, mixing, things like that, then it's like someone saying, is your linear static analysis accurate? Well, if the problem is linear statics, of course it's accurate, as long as I have a mesh independent solution in solid mechanics. So, you know, this wouldn't be released to the market, which it was, I think, 5-ish years ago, unless we were already matching to the expectations. Does that make sense?
Yeah, Jim, that makes sense.
There,
How
there,
would you actually change the geometry on the fly now? Because we've seen all the promo videos, I think at least the majority of people watching.
yeah,
When you can change the geometry on the fly, maybe change the radius, how would that work? Is
yeah,
it then
for sure.
real-time
So
update?
yeah, of course, yeah. So once we hit play on here, I'll give you an example on this model. So I've actually parameterized this model. Okay, so if I turn on, let me just turn on. We've got some more results here. Let me just see if turn the mold off for a second. Oh, the temperature band isn't looking right. So I'll just leave it on the top for a second. So once we solve an analysis, we're never just done with one, right? As we say in our classes, you never hit solve just once. We're always just iterating. Maybe you're iterating physics, maybe you're iterating geometry. So if I wanted to, and from within Explore, while I'm solving, okay, I can just go into the design mode right here. Let's say, for example, I wanted to take, now there's two, just so that we all know what's going on here, there's two surfaces that represent the OD of the fluid and the ID of the mold channel. So there's actually, and it's kind of a nuance of channel flow, there's actually two surfaces in the CAD that we have to manipulate if we wanted to manipulate it. So what I could do is I could say, I'm going to move something. And let's say I want to take this part right here, this sort of bend, and I just want to slide it down. Maybe I want to make it a little bit, if I look at the top here, maybe I want to make it a little bit, further down to see what happens, okay? So I haven't tried this on the fly, so I'm not sure if we're going to see a huge change in the temperature, but let's just say I wanted to move that. Now, I want to move this in a certain direction. So let's just grab, let me come out of my size preview. So there's one of the channels. Let's see, I have to make sure I have which one I have here. That's the mold you can see in the upper left-hand corner, and that's the fluid. So I think I've got both of them. I'm in the move tool, so I'm just going to move the geometry. This is my local coordinate system. Make sure I don't blow through the part. I should be able to just drag this out like this. Let's see if I got them both. I did not get them both. Oh, I did get them both. So automatically it reset the analysis. Just come out of the move tool for a second. $166. I think it was 169 before or something like that. Oh, it looks like we're climbing up to converge towards it. So I don't know if that particular move, right, of the circuit made a massive impact to the temperature, but that was it. Maybe 30 seconds all in. I think there was a small delay in the graphics because I'm sharing my screen as well, which I don't recognize when I'm not. So ultimately, that's that. We've got a GPU-based conjugate heat transfer solver and a direct modeling CAD tool working completely live in unison. That's pretty unique. We've got CAD embedded CFD, we've got CFD embedded CAD, we've got all those combinations before, but usually there's some sort of regeneration on the CAD side, a remeshing, and then a reconvergence on the CFD. And that's all happening on the fly on the GPU. And for those who are curious what hardware I'm working with, right click, task manager, performance. I've got two P4000s. This is like a almost 10-year-old GPU. They're only 8 gigs, but I've got them linked together. And you could probably pick up these today for maybe a couple $100, just for the record, okay? And this is a Dell off-the-shelf workstation from maybe 6 or 7 years ago. Of course, the conversation around GPU you got to talk money sometimes. And although we're not going to talk about like current pricing on GPUs, they can get into the tens of thousands of dollars. You can get into all kinds of dedicated based GPU builds, and it just is just going to get faster and faster and faster. But just so that we're all on the same page here, these are $100, maybe $200 GPUs. I've got two of them that are linked together in a Dell box. There, full disclosure, that's what we're looking at. So that's not
Pretty
bad.
cool.
That was a 30-second, kind of a 30-second update. So I'm just going to pause that right there to rest the GPU for a second. Now, what I've done is I've pre-programmed, or I should say pre-parameterized the model. So what you just saw was a very interactive, very dynamic way to update the model so I can do a what if scenario. But a lot of times what we're doing is a little bit more of a structured what if. And I know you probably heard the term I'm about to say, but we call it in some cases a design of experiments, right? Or a DOE, where we've got multiple variables. Each variable has multiple options or variations, and we then create this multiple dimensional matrix, okay? And that is a great way to apply mathematical concepts. I'm wrapping mathematical concepts around a simulation, around physics, because it's all about the what if. And if you're sitting there doing what if manually, then you are going to be biased, which in engineering, we all have biases, but ultimately the whole purpose of applying statistics and math and doing a DOE is to remove any sort of bias, right? And so I could parameterize the length, I could parameterize the diameter, I can parameterize the material properties, I can parameterize flow properties and temperatures. I can parameterize anything, just like pretty much every simulation tool now you can do that. What I've done is that move that you just saw, okay, that's actually been parameterized I'm going to go back to the model for a second so we can see that. I've actually parameterized two things. So I've parameterized what you just saw, which is moving the bottom of the circuit. So I call it circular bottom distance. And that distance is the distance from this circuit. Let me just look at it from the top for a second. Let me break this out just so we can see what's going on. So what I've done is I parameterized this being moved up and down, okay? And I've parameterized the same thing for the top. So the same thing that I just did, which was move kind of the length of the circuit, right, around and whatnot. And again, this is representative of in conformal cooling, we're trying to play around with how do I get it close to the part, but not too close? Excuse me, how do I make sure that, you know, I've optimized the circuit? So those are the two things that I've parameterized. This is the sort of the current value, if you will. And then when I go into my explore mode to do the simulations, I can take those parameters and I can create an entire set of variations. Okay, so this model right here, I haven't created the variation, so let's just create a couple on the fly, and I'm going to show you what our burst to cloud does. So ultimately, let me just go on this side because this is covering up the nothing that we're looking at. So I've got one design variation. This is DV1. DV1 is just the original sort of location, if you will. This is the distance down here, and this is the distance essentially to the top. And then I'm looking at some outputs. I've got max velocity, which you may or may not care about. That was in automatically. The max system temperature, pressure drop, which is really important for designing the system. And I have what's called ABS Max. ABS Max is created by me, so I can create a monitor. I can create any custom monitor I want on the system. For example, here's a list of the variables that I might be able to create. So I can go all the way down to, you know, quantifying turbulence, right? So pressures, flows, et cetera, uniformity, however that's defined, et cetera. So I can create all that. So what I've created is what's called ABS Max. ABS Max is just what's the maximum temperature on the ABS plastic, okay? I'm sorry if it's confusing. I realize that might seem like it's absolute max. That's actually the max temperature of the whole model. This is the max temperature of the plastic itself. So I haven't gone to the level of creating a difference, but right here, as you can see, I can reference a second location and compute the difference. So in a perfect world, Yusuf, if we were starting this in a few more hours and I could dial this model in a little bit better, we would say, what's the hot side of the mold? What's the cold side of the mold? And what's the difference? And we could optimize this model for minimizing the difference between the hot and the cold. I can always slide those around with my circuit. So, but right now, if you don't mind, we're just doing the maximum of that. And what we can do is we can create variations, right? So just like any other sort of DOE tool, I can create my matrix. So I'm going to select this parameter and I'm going to select this parameter. So I've got my bottom circuit distance and my top circuit distance, and I might have some sort of minimum, say 25 millimeters, a maximum of 75, and I'll have, say, 10, and I'm just hitting tab here, 25, 75, and 10. Create 100 variations. Boom, that's it. So this is a simple, say 2 parameter by 10. So it's 100 to the, or excuse me, 10 to the 2, right? So I've got 100 variations plus the original variation. So there I just created 101 variations. And because it solves really quickly on the GPU, I think we saw maybe 15, 20 seconds, you could infer, oh, wow, great. I can do 15 seconds times 100. I'm going to do, 1,500 seconds. But what if it was a little bit longer, a little more complex, and you're just like, you know what, I want to do 1,000, right? At some point in time, the designer, the analyst, the simulation, the who, whatever you want to call yourself, you just get curious. You get curious beyond whatever hardware you have, right? Either we're cranking up the mesh, which doesn't necessarily apply in this case, or we're cranking up complexity, or we're cranking up variations. We're always pushing for more. So in the latest version, we have the ability to just push to the cloud. And so I can just go to cloud, I can hit update all. And what it does is it links up to our cloud. You may recognize this as a company from a few years ago called OnScale. I don't know if you remember them, but OnScale was an awesome web-based simulation platform. Had a partnership with Ansys and a partnership with a bunch of others. Ansys acquired them, and this, as far as I know, is the first implementation. I don't think it's been shown yet. This just came out a few weeks ago, and this might still be in beta. So this is brand new, but this is the future. This is we're embedding what we call burst to cloud in. I'm not going to submit this right now because that's going to put in 100 to 1 variations. But just for example, if I wanted to just grab, say, 10, we can kind of infer what that might look like. So cloud, update selected, and hit submit. So we're going to see this basically queue up. What's happening locally is we are adjusting the geometry on the fly, and then that new model is being submitted up to the cloud for analyzing. So you can see the geometries live, right? You see how the circuit is updating, and nothing's really. I've in this particular case, the first 10 are all the bottom distance. Or sorry, the top distance is being changed while the bottom distance is not. So this is all updating the geometry and setting up to the cloud on the fly. I wasn't going to have the whole solve happen right now, but it should start to update. It'll run about 4 or 5 or 6 in parallel, which is going to be better than one at a time here. You can see we're starting to get some of the results in now. So it looks like we've got. Let me roll back. There we go. So you can see we're solving 1, 2, 3, 4, 5, 6, 7 in a row right now. We've already got results for the first 4 or 5. So it's relatively quick. We're able to basically in serial, because we're locally doing this with the GPU, changing geometry, and then in parallel, we're sending up to what was OnScale, what is now the burst to cloud feature and discovery at Ansys Cloud, and now we're done. So that was 11 analyses in, I would say, about a minute, maybe less than a minute. So we're averaging what, 6 seconds per. And again, engineers want more, more simulation, more physics, more solving, more geometry, more data. If I wanted to, I could create, say, a graph, right? Because a lot of times that's a great way to communicate our results. And let's say on the x-axis, I wanted to show, say, pressure drop. And let's say on the y-axis, I would show maybe the max temperature of the mold. And you can start to see we're starting to get our optimization curve, right? And so what we're going to be looking for example, is let's say I had some minimum temperature that I wanted to maintain. Well, let's say I wanted to be below, I don't know, in this case, 88.8. This is pretty precise here, but let's say I want to be below some certain temperature. I'll have 3 or 4 or 5 or 6 different designs of our cooling circuit, of our conformal cooling circuit that meet that criteria. So what's the second criteria? Minimize pressure drop. So let's say I wanted this to be below 88 and 88.8, and I want to minimize pressure drop. Then I'm going to go to this guy right here. There it is, set to current. And this is going to update the geometry. Boom. So think about what we just did, right? We solved our conjugate heat transfer model. We sent a bunch of variations to the cloud to get a data quickly. And then we picked up an optimized geometry, and I set that as my latest. I did that, what, in a couple minutes, tops? Including,
yeah, it's pretty cool.
Kind of building it out. So let's, think about that for a second. When we talk about making decisions as an engineer or as a designer using simulation, we've always had this sort of balance, right? This seesaw. Do I want accuracy? Do I want speed? Right? Because usually I have a fixed amount of time to make a decision. Usually my manager, my customer, my client, whatever, is saying, hey, listen, you need to come up with the design in 2 weeks, right? And as I'll say, as an analyst, I don't really deliver a simulation, right? I deliver the results of a simulation to the optimized design. We're delivering designs. We're putting designs into production. We're not putting analyses into production. It's just a tool, right? So how do I get to that optimized design? Well, there's a trade-off, right? If I were to do a simulation that has full physics to 7, to 7 different decimal places, right? It's going to take time. Will it be optimized? I don't know. You got 2 weeks to do it. Good luck, right? And so what if I said you don't need 7 decimal places. You don't need dual precision, right? You just need something that's, say, within 5 or 10%, and you just need to do it 100 times. And that's where the statistics of math come in and say, hey, listen, I don't need to be hyper accurate if I can convince myself that I've got an optimized solution because of the quantity of data that I have, right? That is the decision that we're making right now. We've got big simulations, we've got big data, we've got AI, ML, right? This is all sitting on the desk in front of us. Which of those tools, which combination of those tools do I use to get the optimized design? Because at the end of the day, my customer doesn't care how I got it. The manager doesn't care how I got it. Who cares how I got it, right? I have a choice to use those tools. So what I'm showing you, what I think is what we call a little bit more on, you've heard probably the term shift left or to the left-hand side, right? So the left-hand side of the time scale is how do I quickly make changes, even if I don't have the accuracy? And how do I have confidence that I'm optimizing, even though I don't have a full fidelity, hyper accurate to dual precision analysis? And the answer is you do a DOE. You cram data in there. You try to remove the variables with quantity more heavily weighted than quality. Does that make sense? Everything's a trade-off. So let's fast forward to what would happen if I did 100. So this right here, okay, I just swapped over to another model that I solved late last night. Maybe it was early this morning, but there are 100 solves here that were all done on the cloud, right? I want to say this probably took a couple minutes, right? Just based on what we just saw, right? And what I've got here now is my full data set. So in this case, right, so I've got a slightly different, setup here. I'm controlling my fidelity. In this case, I backed it down a little bit just for speed last night, right? But what I've got is I've got my front of optimization. I've got maybe my limit on what I want this mold temperature to be. Okay, let's say I want it to be below 91, which would be somewhere right in here. Now, any combination, you can see I've probably got a few dozen design iterations. Now I want to, again, which one's the minimum pressure drop? So now this is a data set that as a designer, an analyst, or whatever you want to call yourself, this is a data set you bring to management, right? There are other parameters that haven't been factored in yet, like cost or economical issue, labor. I mean, there's other aspects, maybe not in this particular case, but there's a lot of other things that we can add in. And of course, Yusuf, we're doing that, right? This is just a physics optimization, but you can connect this with Python. We've got OptiSlang. You can hook it all into all kinds of other custom or off-the-shelf code and truly optimize. And again, we may not be doing the highest quality, highest fidelity solve, but we're replacing that time and effort with massive amounts of data, quantity. And statistically speaking, those two things can be equivalent.
That was awesome, Jim. Thank you so much.
Yeah.
What would be the next step for us? Like, do you have any other demos planned that we could cover in a deep dive session? Like, what would be
For
the next
sure,
step?
for sure. I mean, there's a couple different ways that we can take this to the next level, right? So next, let's say, for example, Yusuf and I, you and I were partners on this model, right? And we're building this out. What are the next steps for this particular model? Number one is we could, if, for example, push it to Fluent. So if we wanted to do a workflow on what the latest Fluent looks like, for example, or what maybe a deeper physics might look like, or maybe connecting into OptiSlang if we want to do a physics and non-physics optimization. And again, all of this is feeding into your and my one of our favorite topics, which is AI ML, which is what happens when I want to predict the future. That is engineers' number one goal is to predict the future, right? Because that's what we get paid to do. What's going to happen? If I invest the money in the tooling, if I invest the R&D dollars, then what are we going to get? What's the performance? What's the reliability? And where AI is able to do that is by using an existing mixed data set. So what do I mean by that? Well, AI is only as smart as the data that it's been trained with, right? It's only as accurate and predictable as what you've fed into it. And a lot of companies right now are asking themselves, how do I use AI in engineering? Oh, by the way, I don't have 30 years of test data. The ones who are at the forefront have 30 years of test data and probably 20 years of simulation. So they've got boatloads of data to feed into AI. And now we're getting off the shelf AI tools. Before that, we had in-house AI tools, right? This is the whole point of predictive engineering. But what does a company do when they don't have that continuity of data? And the answer is this. This is what they're doing. They're creating data sets with simulation. So all I have to do is match one of these dots, okay? One of these dots has to match a test. I only have to do one test. At some point, I got to build the mold. At some point, I'm going to put a thermocouple on it. At some point, I'm actually going to make this thing happen, right? I only need to match that one. And I get 99 other data sets to train an AI. So we could continue this conversation, Yusuf, in how do I take a data set like this that's high quantity, okay? And how do I feed this into an AI workflow? Another potential, because I know we talk a lot about AI. There's a lot of stuff out there, but I haven't seen a lot of hands-on how-to sort of deep dives. And then the third aspect of a secondary deep dive on this could be or should be design for additive, right? This particular geometry, I simplified it, but we can talk about how do I then take this if I cannot manufacture it any other way. It's so complex. The conformal cooling channels go all around the part. So complex. I have to do additive. There's a simulation workflow for design for additive for metal, which we have as well. So there's a couple of different ways, Yusuf, that we can take this model and move forward in a couple of different directions. I'm wide open to whatever.
That sounds great. Some people were asking for the slides, so we're going to send them to them, or maybe just contact Jim on LinkedIn.
Yeah, so I think you're gonna have this hosted. I'll have it hosted wherever it's gonna be. We'll send the link out. LinkedIn, of course, is for those who know Yusuf and I. We're very active on, so it'll get linked onto LinkedIn. Look, just keep an eye on Yusuf's account or ours or on Fastways.
Sounds great. We have one last question, and then we can wrap it up. Jim, great stuff. Many thanks. Is the setup and datasets available for comparison?
For sure, I don't see why not. I mean, this is my geometry, but everything. I mean, as far as the data sets go, I can export this to CSV if you want to kind of dig into the data. Unless you've got Discovery, the Disco file won't help. But ultimately, if you want to learn more about the capabilities, the file types, and everything, again, you can reach out to me directly on LinkedIn. I'm on there as Fastway Jim. You can reach out to us at Fastway. Send us an email, jshaw@fastwayengineering.com. We'll get it over to you. We're all about sharing here. There's nothing here proprietary.
Sounds great. Jim, thank you so much, and looking forward to the next session.
Yeah, likewise, Yusuf. Thank you so much, man.
Cheers.
Take care.